let's go back to the boat with the fisherman who's tuned out long ago. Let's talk to the programmer. Let's jump around and go back to CPython that we tried to define as the reference implementation. And one of the big things that's coming out in 3.11, what's the right way to pronounce that?
We tend to say 3.11 because it really was like we went 3.8, 3.9, 3.10, 3.11, and we're planning to go up to 3.99.
99. What happens after 99?
Probably just 3.100 if we
100?
make it there.
Okay. And go all the way to 420. I got it. Forever Python v3. We'll talk about 4, but more for fun. So 3.11 is coming out. One of the big sexy things in it is it'll be much faster. So how did you, beyond hiring a great team or working with a great team, make it faster? What are some ideas that makes it faster?
It has to do with simplicity of software versus performance. And so even though C is known to be a low-level language, which is great for writing sort of a high-performance language interpreter, when I originally started Python or CPython, I didn't expect there would be great success and fame in my future. So I tried to get something working and useful in about 3 months. And so I cut corners. I borrowed ideas left and right when it comes to language design as well as implementation. I also wrote much of the code as simple as it could be. And there are many things that you can code more efficiently by adding more code. It's a bit of a sort of a time-space trade-off where you can compute a certain thing from a small number of inputs, and every time you get presented with a new input, you do the whole computation from the top. That can be simple looking code. It's easy to understand. It's easy to reason about, that you can tell quickly that it's correct, at least in the sort of mathematical sense of correct. Because it's implemented in C, maybe it performs relatively well. But over time, as the requirements for that code and the need for performance go up, you might be able to rewrite that same algorithm using more memory, maybe remember previous results, so you don't have to recompute everything from scratch. Like the classic example is computing prime numbers. Like, is 10 a prime number? Well, you is it divisible by 2? Is it divisible by 3? Is it divisible by 4? And we go all the way to, is it divisible by 9? And it is not, well, actually 10 is divisible by 2, so there we stop, but say 11. Is it divisible by 10? The answer is no, 10 times in a row. So now we know 11 is a prime number. On the other hand, if we already know that 2, 3, 5, and 7 are prime numbers, and you know a little bit about the mathematics of how prime numbers work, you know that if you have a rough estimate for the square root of 11, you don't actually have to check, is it divisible by 4 or is it divisible by 5? All you have to check in the case of 11 is it divisible by 2, is it divisible by 3? Because take 12. If it's divisible by 4, well, 12 divided by 4 is 3, so you should have come across the question, is it divisible by 3 first? So if you know basically nothing about prime numbers except the definition, maybe you go for x from 2 through n minus 1, is n divisible by x? And then at the end, if you got all no's for every single one of those questions, you know, oh, it must be a prime number. Well, the first thing is you can stop iterating when you find a yes answer. And the second is you can also stop iterating when you have reached the square root of n, because you know that if it has a divisor larger than the square root, it must also have a divisor smaller than the square root. Then you say, oh, except for 2, we don't need to bother with checking for even numbers because all even numbers are divisible by 2. So if it's divisible by 4, we would already have come across the question, is it divisible by 2? And so now you go special case, check, is it divisible by 2? And then you just check 3, 5, 7, 11. And so now you sort of reduced your search space by 50% again by skipping all the even numbers except for 2. If you think a bit more about it, or you just read in your book about the history of math, one of the first algorithms ever written down, all you have to do is check, is it divisible by any of the previous prime numbers that are smaller than the square root? And before you get to a better algorithm than that, you have to have several PhDs in discrete math. So that's as much as I know.
So, of course, that same story applies to a lot of other algorithms. String matching is a good example of how to come up with an efficient algorithm. And sometimes the more efficient algorithm is not so much more complex than the inefficient one. But that's an art, and it's not always the case. In the general cases, the more performant the algorithm, the more complex it's going to be. There's a kind of trade-off.
The simpler algorithms are also the ones that people invent first, because when you're looking for a solution, you look at the simplest way to get there first. And so if there is a simple solution, even if it's not the best solution, not the fastest or the most memory efficient or whatever, a simple solution, and simple is fairly subjective, but mathematicians have also thought about sort of what is a good definition for simple in the case of algorithms. But the simpler solutions tend to be easier to follow for other programmers who haven't made a study of a particular field. And when I started with Python, I was a good programmer in general. I knew sort of basic data structures. I knew the C language pretty well. But there were many areas where I was only somewhat familiar with the state of the art. Mm-hmm. And so I picked, in many cases, the simplest way I could solve a particular subproblem, because when you're designing and implementing a language, you have many hundreds of little problems to solve. And you have to have solutions for every one of them before you can sort of say, I've invented a programming language.
First of all, so CPython, what kind of things does it do? It's an interpreter. It takes in this readable language that we talked about, that is Python. What is it supposed to do?
The interpreter, basically, it's sort of a recipe for understanding recipes. So instead of a recipe that says, bake me a cake, we have a recipe for, well, given the text of a program, how do we run that program? And that is sort of the recipe for building a computer.
The recipe for the baker and the chef.
Yeah.
What are the algorithmically tricky things that happen to be low-hanging fruit that could be improved on? Maybe throughout the history of Python, but also now. How is it possible that 3.11 in year 2022, it's possible to get such a big performance improvement?
We focused on a few areas where we still felt there was low-hanging fruit. The biggest one is actually the interpreter itself. And this has to do with details of how Python is defined. So I don't know if the fisherman is going to follow this story.
He already jumped off the boat. He's this. I'm
bored. Yeah,
this is stupid.
Python is actually, even though it's always called an interpreted language, it's there's also a compiler in there. It just doesn't compile to machine code. It compiles to bytecode, which is sort of code for an imaginary computer that is called the Python interpreter.
So it's compiling code that is more easily digestible by the interpreter, or is digestible at all?
It is the code that is digested by the interpreter. That's the compiler. We tweaked very minor bits of the compiler. Almost all the work was done in the interpreter. Because when you have a program, you compile it once and then you run the code a whole bunch of times. Or maybe there's one function in the code that gets run many times. Now I know that sort of people who know this field are expecting me to at some point say, we built a just-in-time compiler. Actually, we didn't. We just made the interpreter a little more efficient.
What's a just-in-time compiler?
That is a thing from the Java world, although it's now applied to almost all programming languages, especially interpreted ones.
So you see the compiler inside Python not like a just-in-time compiler, but it's a compiler that creates bytecode that is then fed to the interpreter. And the compiler, was there something interesting to say about the compiler? It's interesting that you haven't changed that, tweaked that at all, or much.
We changed some parts of the bytecode, but not very much. And so we only had to change the parts of the compiler where we decided that the breakdown of a Python program in bytecode instructions had to be slightly different. But that didn't gain us the performance improvements. The performance improvements were like making the interpreter faster, in part by sort of removing the fat from some internal data structures used by the interpreter. But the key idea is an adaptive specializing interpreter.
Let's go. What is adaptive about it? What is specialized about it?
Well, let me first talk about the specializing part, because the adaptive part is the sort of the second order effect, but they're both important. So bytecode is a bunch of machine instructions, but it's an imaginary machine. But the machine can do things like call a function, add two numbers, print a value. Those are sort of typical instructions in Python. And if we take the example of adding two numbers, actually in Python, the language, there's no such thing as adding two numbers. There's just the compiler doesn't know that you're adding two numbers. You might as well be adding two strings or two lists or two instances of some user-defined class that happen to implement this operator called add. That's a very interesting and fairly powerful mathematical concept. It's mostly a user interface trick, because it means that a certain category of functions can be written using a single symbol, the plus sign. Mm-hmm. And sort of a bunch of other functions can be written using another single symbol, the multiply sign. So if we take addition, the way traditionally in Python the add bytecode was executed is pointers, pointers, and more pointers. So first we have two objects. An object is basically a pointer to a bunch of memory that contains more pointers.
Pointers all the way down.
Well, not quite, but there are a lot of them. So
yeah.
To simplify a bit, we look up in one of the objects, what is the type of that object, and does that object type define an add operation? And so you can imagine that there is a sort of a type integer that knows how to add itself to another integer. And there is a type floating point number that knows how to add itself to another floating point number. And the integers and floating point numbers are sort of important, I think, mostly historically, because in the first computers, you used the sort of the same bit pattern, when interpreted as a floating point number, had a very different value than when interpreted as an integer.
Can I ask a dumb question here?
Please do.
Given the basics of int and float and add, who carries the knowledge of how to add two integers? Is it the integer?
Type.
It's the type integer versus...
It's the type integer and the type float.
What about the operator? Is the operator just exist as a platonic form possessed by, by the integer?
The operator is more like it's an index in a list of functions that the integer type defines. And so the integer type is really a collection of functions, and there's an add function, and there's a multiply function, and there are like 30 other functions for other operations. There's a power function, for example. And you can imagine that in memory, there is a distinct slot for the add operations. Let's say the add operation is the first operation of a type, and the multiply is the second operation of a type. So now we take the integer type and we take the floating point type. Mm-hmm. In both cases, the add operation is the first slot and multiply is the second slot. But each slot contains a function, and the functions are different because the add two integers function interprets the bit patterns as integers. The add two float function interprets the same bit pattern as a floating point number. And then there is the string data type, which again interprets the bit pattern as the address of a sequence of characters. Mm-hmm. There are lots of lies in that story, but that's sort of a basic idea.
I could tell the fake news and the fabrication going on here at the table. But where's the optimization? Is it on the operator? Is it a different inside the integer?
The optimization is the observation that in a particular line of code. So now you write your little Python program. Mm-hmm. And you write a function, and that function sort of takes a bunch of inputs, and at some point it adds two of the inputs together. Now, I bet you even if you call your function 1,000 times, that all those calls are likely all going to be about integers, because maybe your program is all about integers. Or maybe on that particular line of code where there's that plus operator, every time the program hits that line, the variables A and B that are being added together happen to be strings. Mm-hmm. And so what we do is, instead of having this single bytecode that says, here's an add operation, and the implementation of add is fully generic. It looks at the object. From the object, it looks at the type. Then it takes the type and it looks up the function pointer. Then it calls the function. Now the function has to look at the other argument and has to double check that the other argument has the right type. And then there's a bunch of error checking before it can actually just go ahead and add the two bit patterns in the right way. What we do is, every time we execute an add instruction like that, we keep a little note of, in the end, after we hit the code that did the addition for a particular type, what type was it? And then after a few times through that code, if it's the same type all the time, we say, oh, so this add operation, even though it's the generic add operation, it might as well be the add integer operation. And the add integer operation is much more efficient because it just says, assume that A and B are integers, do the addition operation, do it right there in line, mm-hmm. and produce the result. And the big lie here is that in Python, even if you have great evidence that in the past it was always two integers that you were adding. At some point in the future, that same line of code could still be hit with two floating points or two strings, or maybe a string and an integer.
It's not a great lie. That's just the fact of life.
I didn't account for what should happen in that case in the way I told the story.
There is some accounting for that.
And so what we actually have to do is, when we have the add integer operation, we still have to check, are the two arguments in fact integers?
Yeah.
We applied some tricks to make those checks efficient. And we know statistically that the outcome is almost always yes, they are both integers. And so we quickly make that check, and then we proceed with the sort of add integer operation. And then there is a fallback mechanism where we say, oops, one of them wasn't an integer. Now we're going to pretend that it was just the fully generic add operation. We wasted a few cycles believing it was going to be two integers, and then we had to back up. But we didn't waste that much time, and statistically, most of the time, basically, we're sort of hoping that most of the time we guess right, because if it turns out that we guessed wrong too often, or we didn't have a good guess at all, things might actually end up running a little slower. So someone armed with this knowledge and a copy of the implementation, someone could easily construct a counterexample where they say, oh, I have a program and now it runs 5 times as slow in Python 3.11 than it did in Python 3.10. But that's a very unrealistic program. That's just like an extreme fluke.
It's a fun reverse engineering task, though.
Oh, yeah.
So there's
people do that stuff.
People like fun, yes. So there's some presumably heuristic of what defines a momentum of saying, you seem to be adding two integers, not two generic types. So how do you figure out that heuristic?
I think that the heuristic is actually, we assume that the weather tomorrow is going to be the same as the weather today.
So you don't need 2 days of the weather?
No. That is already so much better than guessing randomly.
So how do you find this idea? Hey, I wonder if instead of adding two generic types, we start assuming that the weather tomorrow is the same as the weather today. Where do you find the idea for that? Because that ultimately, for you to do that, you have to kind of understand how people are using the language, right?
Python is not the first language to do a thing like this. This is a fairly well-known trick, especially from other interpreted languages that had reason to be sped up. We occasionally look at papers about HHVM, which is for Facebook's efficient compiler for PHP. There are tricks known from the JVM, and sometimes it just comes from academia.
And so the trick here is that the type itself the variable doesn't know what type it is. So this is not a statically typed language where you can afford to have a shortcut to saying it's ints.
This is a trick that is especially important for interpreted languages with dynamic typing, because if the compiler could read in the source these X and Y that we're adding are integers, the compiler can just insert the single add machine code, that hardware machine instruction that exists on every CPU, and ditto for floats. But because in Python you don't generally declare the types of your variables, you don't even declare the existence of your variables. They just spring into existence when you first assign them. Mm-hmm. Which is really cool and sort of helps those beginners, because there is less bookkeeping they have to learn how to do before they can start playing around with code. But it makes the interpretation of the code less efficient. And so we're sort of trying to to make the interpretation more efficient without losing the super dynamic nature of the language. That's always the challenge.